Hello, everyone. Welcome to today's sessions of the GLAZE webinar series entitled LED Basics Applied to Horticulture Lighting Systems. The GLAZE Consortium webinar series is a selection of live recorded online presentations that cover a broad range of topics at very technical levels and scale. These webinars feature the latest technology innovations and best practice in the CEA field, providing the audience the opportunity to discover new solutions and to connect with field experts. I would like to introduce you to today's presentation, Dr. Robert Karlicek. Hello, Bob, and thanks for being the presenter today. Dr. Robert Karlicek is the director of the Center for Lighting-Enabled Systems and Application at Rensselaer Polytechnic Institute, an NSF and industry-funded program exploring advanced applications for next-generation solid-state lighting systems. Prior to joining RPI, he spent over 30 years in industrial research and R&D management positions with corporations including AT&T, Bell Labs, and General Electric. His technical expertise includes epitaxial growth of high-performance LEDs and lasers, advanced device fabrication and high-power LED packaging, thermal management, control systems design and applications research in solid-state lighting, as well as other novel LED uses such as infrared and UV LED applications, wireless communications using lighting, known as Wi-Fi, and advanced LED displays applications. Dr. Karlicek obtained his Ph.D. in physical chemistry from the University of Pittsburgh and has over 56 peer-reviewed technical papers and 44 US patents. He is the founder and president of SolidUV Incorporation and sits on the technical advisory board of several high-tech startup companies. Dr. Karlicek is also a GLAZE researcher at RPI. A recorded version of this webinar will be available at our website at glaze.org. If you have any questions about the presentation or if you'd like to get in contact with the speaker, please submit your inquiries using the chat box. We have a chat box and a Q&A box. We will do our best to answer all your questions at the end of the presentation. Now, I would like to pass the word to Dr. Karlicek. Bob, thanks for being the presenter today, and I look forward to see your presentation.
Thank you, Erico, and thanks to everybody that's attending this call. And it was a nice opportunity to put together a few high-level overviews of the technology of light-emitting diode systems, with a particular focus on how the LEDs are actually used in horticultural lighting. And I'm going to primarily focus on the state of the LED technology that is being developed today, not only for horticulture, but for solid state lighting, but we'll talk primarily about applications in the horticultural space. So this is an outline of the talk I'd like to kind of cover. I'm going to do a very basic overview of LED science and manufacturing to try to give everybody an idea of where LEDs come from. Talk a little bit about full spectrum considerations in LED development. I want to address a little bit some of the prospects for higher efficiency and lower cost light emitting diodes, particularly in the field of horticulture. Say a few words about UV LEDs and clear up a few things about what UV really is and how it's typically used by people in the LED space. Talk about some LED advantages that we see for the future of horticultural lighting, then summarize and have some open discussion about some of the things that are going on in the LED field. So let's start with the basics. In the top right side, you see the periodic table, and inside the big red box are the elements that we use to make materials that we know as semiconductors. Properly combined, these materials are neither insulators or conductors like metals, but can be used to make materials which are in between, partially conducting. We know silicon from the computer chip world as probably one of the best and highest volume semiconductors that are around. This is an elemental semiconductor, silicon, in column 4, right underneath carbon. But silicon cannot be used to make light. It is what we call an indirect bandgap semiconductor, and it's not capable of generating photons. It's the compound semiconductors that we make from columns 3 and columns 5 of the periodic table, the topping with boron and nitrogen, shown just below that are used to make light-emitting diodes, lasers, certain kinds of solar cells, and they can also be used for electronics. And then within that box, there's another class of semiconductors that are typically used to make detectors and solar cells, the 2,6 compounds, and we're not going to really talk about those today. They can make LEDs, but today's modern LEDs are made from 3, 5 compounds. And of course, the 3 and the 5 refer to the columns of the periodic table. The periodic table top with boron being column 3, and the periodic table column topped by nitrogen is column 5. And we can mix and match these different compounds, which are typically binary compounds, in different ways to control the wavelength of light generated by an LED. So for example, in the compound semiconductors, I can pick the element gallium, and I can combine that with nitrogen and make gallium nitride. Gallium nitride is the base semiconductor compound used for making blue light-emitting diodes. And typically to make them blue or to make them UV, I would put varying amounts of aluminum and indium into the gallium nitride to make what we would call an aluminum indium gallium nitride alloy. And that's how I make a blue LED. For red or far red light-emitting diodes, I don't use the nitrogen in the periodic table. I use the phosphorus. And there I would work with aluminum indium gallium phosphide to make red and far red light-emitting diodes. So because we can alloy these elements in different compositions, different fractions, we have a great deal of ability to control the wavelength that we generate with light-emitting diodes. So that's kind of the very beginning of LED basics, semiconductors, 3,5 compounds. The growth supply chain kind of looks like this a little bit to give you an idea of where they start off with. All LEDs are crystalline devices. The best semiconductors are crystalline devices. And they're heavily engineered, just like you would make silicon or computer chips in a wafer form. We start off with wafers to be able to make LED structures by growing crystalline materials on a substrate. So shown in the top left in the material processing side, where we make the chips, there's a LED wafer that actually happens to be a 6-inch diameter wafer being probed to make blue light. That's what it would look like coming out of the crystal growth machine to be able to make blue LEDs. Red LED wafer would look very similar, except it would appear black. And depending upon the composition, it would emit red or far red light. Now, this wafer can be fabricated and made into LED chips. That's the next picture over. That would be a representative example of either a red or a blue LED chip in its bare form. And there are a lot of chip companies today that make these LEDs, but generally speaking, there are just a handful of companies that make all the different colors of LEDs that can be used for horticultural lighting. Most LED companies focused on blue light-emitting diodes and now UV light-emitting diodes using gallium nitride because of the interest in solid-state lighting, your LED light bulbs and the like. There are a handful of companies that make all the colors of the rainbow, typically in volumes that they can sell them in. And I'm kind of going down the bullet list there of things under LED chip companies. Now, LEDs have been around for a while. Volume production is critical for these LED chip companies. Their margins are very, very low. So high volume, low volume manufacturing is critical for LED chip suppliers. The cost of entry is very, very high. It's not easy to build a semiconductor fabrication facility. A typical LED semiconductor fabrication facility might cost on the order of $1 to $5 billion to be able to make. It's not for the faint of heart. And the only point that I kind of want to make, and I'll reiterate this later, is that the overall efficiency, the micromole per joule, if you will, in these LED chips is starting to near theoretical and, for all intents and purposes, practical limitations. These are highly engineered systems. Now, ordinarily, LED companies make the chips and they sell the bare chips in a wafer form to a packager. The packager takes these LED chips and puts them into a package. A representative package is shown in the third image over here on the side. This happens to be a white LED, and you can tell it's white because it's got a phosphor on it. There are very few packagers that make their own chips. There are a few that do. Osram would be an example of an LED company that makes their own chips. So would Lumileds. Cree would be another example of the company, but most companies in the world buy their chips from somebody else and put them in the package. And then as we progress to the right-hand side, full system integration, lots of players, very, very few of the fixture integrators make their own packages. None of them make chips. And so it's rare that the fixture manufacturer is fully integrated from soup to nuts, making the semiconductor materials, the dice, the die, and the package, and the LED fixture. Keep in mind that one LED wafer can yield tens of thousands of small LED die. Each one of them is individually tested, sorted into power levels, packaged, and then shipped to fixture manufacturers. And so this would be a typical supply chain. The manufacturing is rather complicated. I would say that the highest tech component is in the chip portion of the device. Technology level of interest and difficulty of entering goes down as you go to packaging. There are a lot of packaging companies, and fixture barriers to entry are very, very low. Almost anybody can get into the fixture manufacturing business and make horticultural lights or make solid state lights for that matter. So if we want to take a look at what's in a typical LED wafer, we want to understand what tends to make the chips so expensive. It is really a very complex growth process. Going back to blue LED wafers, where I have most of my own personal growth experience in making LED die. This would be an example of our 3,5 compound semiconductor gallium nitride. The P and the N refer to impurities that are added to make the diode. And it's that pink line across the structure that is where all the light gets made. And to give you an idea of what a fine resolution image of that structure looks like, you can take a look at this blue LED shown on the right-hand side. You'll notice that the dimensional bar over here is 20 nanometers. And the light comes from these dark lines that we call quantum wells. That's where all the light comes from. Each one of those layers is grown just a few atomic layers at a time, and growing this entire structure that is shown over here in this figure might take on the order of 3 or 4 hours to be able to get out the LED wafer. Of course, it's grown on sapphire. Sapphire is the crystal growth template, and this is where we are actually growing the LED wafer. Fabrication time of the entire wafer to chip is about 2 weeks. In the LED manufacturers right now, costs are pretty much squeezed out. There's not a lot more room for cost reduction. And in fact, the margins for LEDs, whether they're for lighting or for horticulture or for sensing, are really very, very low. And they're almost 100% made in Asia. Now, if I go back just a second, there are a couple of companies that actually make the LED wafer in the United States, but they ship it to Asia for making the chip, and then the packaging is done usually in Asia. And those packages can come back to the United States, sometimes China, sometimes Mexico, other places, to make the actual fixtures. So the globalization of the LED business is very, very well established. And that's kind of what's in the LED wafer. That's the starting point. This process of growing these layers is called epitaxy. Epi and taxi comes from the ancient Greek for ordered upon. It's how we do the crystal growth for semiconductors. Now, I said that they are semiconductors, and what I kind of want to convey in this slide is what we mean by a semiconductor. And if you take a look at this diagram up over here, we have what we would call a semiconductor. There is a part of the crystal structure which is full of electrons, a part of the crystal structure which has no electrons in it, and there's an energy gap here where there can be no electrons. By changing the chemical composition of indium and gallium and nitrogen, or aluminum, indium, gallium, and phosphorus, I can control the thickness of this band gap. And what I do when I put current into an LED is that I actually put an electron into the empty band. It relaxes to a low energy state through the forbidden band. And that forbidden band or forbidden gap over here is where I make my light. So it's the composition of the semiconductor which governs the energy range of this forbidden band and controls the wavelength of light I get out of the semiconductor. We call this electron-hole recombination for light-emitting diodes, but it's why LEDs are monochromatic. The color of every LED is set by the crystal structure that determines the energy width of this forbidden gap in the semiconductor. Now, if we just take a look at the LED color space that's down over here, we have wavelength down over here, and we have luminous intensity over here. And these are some of the kinds of LEDs that are made in the industry today. I should mention, for anybody who's a real historian buff, the first electroluminant device was made in silicon carbide in 1907. It was written up and published, but it was a good 40 years before anybody really understood how a silicon carbide diode actually made light. It was in the 1950s that a company called Monsanto, who was growing LED materials at that time, started growing other materials. And in 1962, at GE Research Labs, Nick Holonyak, who is currently a professor emeritus at the University of Illinois, made the first red light-emitting diode out of this material right here, a gallium arsenide phosphide. The brightness was very, very low. And then from 1962 to about the 1990s, the aluminum, indium, gallium phosphide class of light-emitting diodes were made. They're very, very bright, and they can make typically the colors red, orange, and yellow. They're not very good at making green LEDs. But if you have a keyboard or a stereo or something like that, and it's got a little green indicator on light, it's the aluminum, indium, gallium phosphide or gap diode that is used to make the green. The efficiency is not very good because this material system cannot make high efficiency green, can't make blue, can't make UV light emitting diodes at all. These LEDs down over here are all low brightness indicator die. In the 1970s, the very first gallium nitride light emitting diodes were made at RCA Research Labs outside of Princeton, New Jersey. They were not very bright. They were not easy to make. A lot of the world gave up on them for a while until the early 1990s. Researchers in Japan, most notably Suji Nakamura, figured out how to make really high brightness indium gallium nitride light emitting diodes. And in fact, in 2014, Suji Nakamura and his two co-workers in Japan got the 2014 Nobel Prize in Physics for figuring out how to complete the spectrum. So we have the indium gallium nitride for the blue and green, the Al-in gap, as we call it, for the red, far red, and orange, yellow. And now we can make visible light all across the spectrum. The original efficiency of these LEDs was not very high. So starting in the 1990s and going all the way up to this day, people have been trying to improve the overall efficiency of lead emitting diodes by optimizing the layer structure that we talked about here, purifying the materials, experimenting with ways of growing these materials, to the point now that these LEDs are extremely efficient. And it's very, very difficult, in my mind anyway, to think that we are going to see much more improvement in luminous efficiency. Now, the DOE is pushing on a few things that might be interesting from a research perspective, but the problems that have existed in LEDs, I'll talk about a little bit later in terms of going to even higher efficiencies, have been around for 25 or 30 years and have resisted solutions by some of the brightest people in the world working on LEDs. Now, for horticulture, I can get UV and blue LEDs from indium gallium nitride. If I take out the indium, I go into the UV. If I add more indium, I go from blue to blue and green. The far and far red LEDs are aluminum indium gallium phosphide LEDs. And for the horticultural lights that you see with LEDs today, what we would call full spectrum lighting, they're usually going to involve red LEDs and full spectrum LEDs that use a phosphor to generate a certain amount of white light. And we'll talk about that in a second, because the phosphor gives you the other wavelengths. I know that a lot of horticultural lights early on were comprised of a blue LED and a bunch of red LEDs. They kind of looked purple when in operation. But nowadays, most of your LEDs are actually white LEDs, so you can get full spectrum lighting from the LED itself. You add an extra red LED to get more photons in the red, and you get your horticultural lighting, generally speaking, in that way. So all of these LEDs are in use today for full spectrum horticultural lighting. Now, I wanted to say just something about the LED binning itself and testing. So usually what happens, if I go back over here at the beginning, I come to a wafer. When I pull that wafer out of my reactor and I send it to the fab and I make a lot of chips, I still have a full wafer full of chips before I dice it into individual wafers. It's almost like a wafer sawing machine. But before I do that, I test 100% of the LEDs using probes to measure the brightness and the overall performance of the LED wafers. And I do that because there are some yield problems when I make my wafer. Not all LEDs on the wafer are created equal. And I'm not going to focus necessarily on anything other than this output power over here. This is a map of my wafer. There are tens of thousands of LEDs that have been mapped. The individual power levels have been measured, and you see that it's not uniform across the wafer. And this is a big problem for LED people. It's a big problem for lighting folks. It's a big problem for horticultural growers, because it means I have to be careful about what LEDs I buy to be able to get full power, high efficiency output. So all the wafer manufacturers test all their LEDs. They dice them into individual chips. They use this XY map to sort the LEDs into wavelength and brightness, what they call bins. And you can kind of see this in this LED data sheet from a very large horticultural LED supplier. In this particular case, this would be Epistar. They are located in Taiwan. And I want to draw your attention to this particular circle over here, where I talk about radiant flux. It's measured in milliwatts, so I can convert that directly to micromoles of photons. And you'll notice that in this particular power LED, they have 3 brightness bins. And you'll note that depending on how I buy my chips, I can get lower brightness or higher brightness, sometimes coming from the same wafer. And what we're starting to find in solid state lighting, and I think we're going to find the same thing in horticultural lighting, is that when a horticultural lighting company or even a lighting company make an LED fixture, they make an ideal prototype, they test the living daylights out of it, they make it from the best LEDs they can find, and then to drive down the cost, they start buying LEDs from the entire bin distribution. So not every fixture will have the same brightness unless They pay a premium price for just the brightest LEDs, and they test everything and have very good quality control at the fixture level. I think we need to do a lot more testing of horticultural fixtures just to find out what the variation from fixture to fixture is going to be. But I will say that in the lighting business, lighting designers will tell you that they can buy 200 fixtures for an apartment building and find a significant variation in brightness from fixture to fixture or efficiency from fixture to fixture. So the industry still has a lot to learn in terms of standardizing the power output and doing that at a cost-effective level. Now, a little bit about the packaging. And I kind of picked this particular image because it's a brand new package that's just released by Osram for horticultural lighting. And I wanted to highlight a couple of the features of the package in a state-of-the-art package. Here's our LED chip sitting inside this package. It's got wire bonds attached to it. That's how I get the current in, get the current out. And it's sitting underneath a silicone lens. The silicone lens is important because it helps remove the light from the chip and get it out into the environment. The shape of this lens is important because it helps reduce reflection in terms of moving the light from the inside of the lens to the outside world and to the plant. A lot of your modern LEDs today will have electrostatic discharge suppression. They are very static sensitive, so if you're handling the LEDs, you have to be careful with that. I should mention one other thing about the silicone lens. Don't push on it with your finger because you can actually break those wire bonds. And in fact, if you get a data sheet from any of the LED manufacturers, they will tell you, don't push on the lens because that's a failure mode for a lot of these structures. You'll notice that this new Osram Oslan Square Hyper Red packaged LED can deliver up to 4.6 micromoles per joule for horticultural lighting applications. And this package was just announced a couple of days ago. So these are the parts of a state-of-the-art package. We can have a blue LED in the same package. We can have a phosphor converted LED in the same package. But keep in mind that this number of 4.6 micromole per joule efficiency is at the LED chip level. My bet would be that the efficacy in the fixture will be lower for various thermal and optical reasons, maybe around 3.7. This is still a really good number for LED lighting. And so contrary to my first original statement that I don't see a lot of upside, there's still some. The LED fixture companies and the LED manufacturers are looking to squeeze every photon out of these LED chips and the LED packages to make them as energy efficient as possible. It's just that they're running out of places to squeeze. Now, there are lots of other packaging styles, shapes, sizes, including multi-chip packages that I'll mention a little bit later. But I think it's fair to say that 100% of all LED packaging is in Asia. The majority of it is in mainland China. Malaysia is probably second, Korea, Singapore, even India is moving into the semiconductor packaging world as the labor costs in China are becoming too high for the LED lighting market. So there's some cost down capability in terms of going to countries with lower labor costs for packaging. But in China already and in Malaysia, these packaging lines where you pick up the chip, put it on the substrate, put the dome on, or put the wire bonds on and put the dome on and then test it again. These are highly automated systems in some of the higher end packaging companies. So again, not a whole lot of opportunity for cost down in the LED manufacturing business. So two areas where we can really take a look at improving the performance of LEDs. And this is a spectrum that we use for some of our research lights here at RPI. I'll mention a little bit. There are two areas that we can work on primarily in the blue and green LED region. The red LEDs, particularly the red LEDs around 660, they're just really very well optimized. There are a few things that people can do to improve the overall efficiency of the chip a little bit more, but I do not see it getting any better, because all of the tricks that people talk about adding to those red LEDs to make them even a little bit more efficient at a tremendous amount of cost. So I don't see them really going anywhere. The big improvements remain over here in the blue and the green. The first big problem with blue LEDs is something called droop. It simply means that as you put more current into the LED, it gets less efficient, even if it doesn't get hotter. There are very sophisticated quantum mechanical arguments for why that happens. It doesn't really happen with red LEDs. It's a very hard problem. It's got the biggest potential for efficiency improvement, but as I said, researchers have been doing it for over 25 years. It's a very hard problem to solve. The next problem with the LEDs is what we call the green gap. If I want to make a full spectrum tunable LED source for horticulture and I want a green LED in there, you can see the total flux density that I get from the state-of-the-art green LEDs is pretty low. This is because it's really, really hard to make green LEDs. And researchers have been working this problem for a long period of time. And we're trying to figure out how to make better green LEDs so we can get values that are up over along with the blue and the red light emitting diodes. But again, this problem has been around for a long time. Now, I want to tie this into the expectation that these problems will be solved. Remember, I said that the margins for state-of-the-art LED manufacturing are very, very low. LED suppliers have very, very little incentive to invest more research on the improvement of LEDs because they're already A, very, very efficient, and B, they can't recoup those investment costs in terms of the sales because nobody's going to want to pay more money for a few % more photons out of the device. So this is going to be another reason why it's going to really be hard to drive even higher levels of efficiency performance. Now, if I want to address the green gap, what other people are doing right now, adding phosphors to be able to convert some of the blue light to green light using a down converting phosphor, just like they make white LEDs for general lighting, and more people are doing that. In a research perspective, notice that I have a fairly narrow emission peak for the green light coming from the LED, but if I have a phosphor converted green, it's a very, very broad emission peak. And so that's one way to differentiate phosphor converted green from direct emitting green, which aren't as efficient. Speaking of phosphors, now this is a slide that I pulled from my work in general lighting. So I'm expressing correlated color temperature over here, cool white versus warm white. I could have different phosphor blends for horticulture. I typically would add phosphor to fill in the middle region to make the lights white-ish. I still can have a lot of blue, and then I can put a red chip in the package or a red chip in the fixture to get a red peak over here to optimize the spectral power distribution for solid state lighting. What the phosphor kind of looks like is shown over here. This is an old style LED in cross section lit up with ultraviolet light. Here's my LED chip. You can see it has two wire bonds to it, a positive bond and a negative bond to get the current in. And then there's this yellow powder sitting over the chip. Some of the photons go into the powder. It converts the powder converts those photons from blue to yellow, and then the yellow light comes out. Some of the blue light comes out directly. Blue plus yellow makes white. So that's how I can get full spectrum lighting. This is now very popular for a lot of the horticultural lights that I'm beginning to see. You can kind of design it so you get a one spectrum fits all. And by fits all, I mean suitable spectral power distributions for all kinds of plants that you may be growing in your vertical farm or your greenhouse, and includes a reasonably good white light for workers, because I know people have complained about having workers working under purple lights too much. And there are probably a lot of different ways of managing that from a greenhouse design perspective. So we're starting to see phosphors creeping into horticultural lighting a lot more. It's a very good way to get full spectrum or spectrum filling in this region over here and make white light and supply all the wavelengths that are required for plants. because as Tessa Pocock, who used to be at Glaze, used to tell me, and I learned a lot about LED lighting for horticulture from her, all the wavelengths really get used by the plant. It's more than just blue and red. So prospects for LED improvement, well, in terms of micromole per joule, red and blue LEDs are approaching their theoretical efficiency. I mentioned there are a couple of wild cards. One is solution for droop in the UV and blue wavelengths, kind of unlikely in my opinion. Another wild card, and the Department of Energy is starting to consider this, higher index, refractive index encapsulants for LEDs might be able to squeeze out another 10%, especially in phosphor converted LEDs with better silicones that do a better job of getting the light out of the LED. In terms of micromoles per dollar, or what we call flux for bucks, LEDs are about as cheap as they're likely going to get in the near term. The largest opportunity for cost reduction in LEDs are at the fixture level and at the system level. So we'd love to be able to get rid of the driver that we have in every LED fixture. One way to do that might be high voltage networked control, where you have a single power supply powering all your LEDs. I know that people are starting to take a look at that. Higher volume adoption of LED lighting in horticulture. If we build up the volume of people making the fixtures, we might be able to drop the cost down to where it's actually more of a commodity. For people in the lighting business, buying LED lighting fixtures for apartment buildings or for commercial spaces. This is a big problem for lighting companies. They're being commoditized to within a very low margin level. That's one way to drive down the cost of horticultural lighting. And I'll hold out that there's a lot of room for innovation in new and cheaper fixture assembly processes, better materials, better optics, better assembly practices. This is where we might be able to save micromole per buck for driving down the cost of LED fixtures for the horticultural lighting field. But I do not expect that anybody's going to be able to squeeze the LEDs of the LED companies much more. One of the other things that I should mention is that over the last 4 or 5 years, the Chinese chip manufacturers have been making very, very cheap light emitting diodes. They've been competing extremely well against LEDs made by Osram and Lumileds and others, largely because the manufacturing costs were underwritten by the Chinese government, either the local government or by the central government out of Beijing. Those subsidies are ending, and so it's not clear that we're going to be able to keep getting those really cheap LED packages for horticultural lighting in China. I don't really know enough about how tariffs have impacted these products to talk about that. Probably some of the people that are lighting fixture manufacturers can address that. Now, I wanted to say a couple of words about UV light emitting diodes. I know that people talking about cannabis and some other plants talk about UV. I just wanted to differentiate the different kinds of UV that are available in terms of LED chips that are made today and clarify what they do and what we mean by UV. So generally the industry in UV light tend to define UV into 3 relatively broad wavelength categories. UVA, which is from 350 nanometers to 400 nanometers. In this commercial range, LEDs are most common at 365 nanometers, 385 nanometers, and 405 nanometers. Remember, LED companies have to bin and test everything, so they like to optimize the wavelengths that they can sell a lot of. I can actually make any wavelength I want. It's just that certain wavelengths are the most in demand. They make them at higher volume so you can get them at better cost. There's the UVB region, which goes from 285 nanometers to 315 nanometers. LEDs in this range are used for either germicidal purification applications. and in some cases in medical applications for treating acne. These LEDs are pretty expensive and highly specialized. And then you've got UVC LEDs from 100 nanometers to 280 nanometers. LEDs are available down to 250 nanometers now, but the most popular ones are at 265 nanometers. Those are ones that are used for germicidal applications. They can kill fungi, they can kill bacteria, and they can kill viruses. And so there's used over there. Now, just a couple of other notions about UV. If you want to get your vitamin D from sunlight, you're getting it from around 300 nanometers. That's mostly where vitamin D comes from in sunlight when it's absorbed by human tissue. Are we ever exposed to UVC radiation? No, because no UV from the sun, and there's lots of it, but no UV from the sun below 300 nanometers gets down to the Earth's surface because it's absorbed in the ionosphere. And in greenhouses in particular, or in buildings with glass windows, there's almost no UV below 350 nanometers that comes through glass. And so generally speaking, what I think people talk about when they talk about UV LED is really taking a look at, I apologize for my little pop-ups here, looking at wavelengths that are going to be in this region of UVA over here. Although people are looking at UVC LEDs to kill powdery mildew, other kinds of problems that plants tend to have in greenhouse, and that's a whole nother kettle of fish. So usually when we talk about UV in the lighting world or even in the plant growth world, we're talking about these kinds of wavelengths. They're not as efficient as blue LEDs. They're more expensive than blue LEDs, but by and large, they're available with good quality and at high volume. As I mentioned, UV LEDs are available down to about 250 nanometers, but UV LEDs are more pricey, tend to have lower reliability, especially the UVC LEDs. One of these chips at 405 nanometers I might be able to buy for about 20 cents, maybe a little bit less at chip level. The UVC LED, same size, lower power, lower reliability, and maybe 100 times more expensive. So more and more LED companies are focusing on this because that's where they can make money. So a couple of things that I want to just address quickly. LED advantages, of course, color tuning. We can optimize spectrum to plant type, more suitable for vertical farming possibly, or for modifying a solar spectrum in the greenhouse. Glaze is working on that now. Advantages include impacting growth rate, nutritional value, flavor control. Issues are complex growth optimization, complex control. Color mixing is a big challenge, and cost. It's easier to get one size fits all with a broad spectrum and just take what you get in terms of the plant growth process that you've got. Although in the future, this may change. I believe if you're in glaze, you've heard about the research lights that we use here, where we use 6 different colors, all in the same LED package for good color mixing. We developed these LEDs primarily for research purposes to take a look at optimizing spectrum for optimized plant growth. Another LED advantage is pulsing, and more people are starting to take a look at this. What I've shown over here on the right-hand side is something called the Koch cycle in photosystem 2. These are all the light, where the light is the little lightning arrow over here, electron exchange reactions that happen in the plant. And you see that each one of these steps has a certain time frame associated with it. Now, people have been working on pulsed LED lighting with plants for a while, but most of the experiments that have been published are not very sophisticated. People are starting to do work on interesting pulse patterns for light-emitting diodes. And I wanted to call your attention to this one particular patent over here that was published in early last year, 2019, from Once Innovations, where they've claimed that a special pulsing format designed to match the photosystem 2 timing was able to increase growth rates of plants by 50 to 100%. Now, I should mention that Once Innovation has been purchased by Signify, also formerly known as Philips Lighting. And I know for a fact that Philips is doing a lot of research on pulse lighting right now to take a look at whether or not they can really validate this approach to trying to improve plant growth rate by trying to time the light to manage the photosynthesis. So that's going to be a very interesting research area going forward that I think that we can kind of take a look at for LED advantages down the road. So I've gone a little bit longer than I thought I would. So it's just quick summary and discussion. LED devices are highly developed, very limited energy efficiency improvement upsides, and very limited cost reduction potential. I think horticultural lighting costs can come down, but the LED chip price itself really won't. The greatest potential for cost reductions at the system level by integrating fixture design and the growth facility integration. I think it's going to take some time to realize that. And then for vertical farming, there are going to be LED upsides on color tuning and pulsed operation. May be useful in the future, but complexity and cost of those kinds of more complex lighting management systems are going to need to be addressed in the future. So with that, I will end my talk and open it up for any kind of questions from the chat boxes that have been developed in the course of the presentation. Thank you, everybody, for your attention.
Thanks, Bob, for the presentation. Great talk, lots of information. We did receive a few questions here, and we have about 10 minutes for discussion, so I think that'll be great. The first question that I have here, they were talking about, just for clarification, on chip versus package makers. Osram, Lumileds, and Cree do both. Are examples of exclusively chip makers along the lines of Samsung?
Samsung makes blue LEDs. They do not make red LEDs. Samsung makes some chips for solid state lighting. I do not know specifically what Samsung is doing in the horticultural space. Samsung does do packaging. They also buy a lot of chips because they don't have the wafer growth volume, epitaxial growth volume to make all their own chips. So I don't know what their mix is. And that's common for a lot of the well-known LED companies. It may not be that LED's company's chip inside that LED's company package. That's also true for Cree. Cree does not make red LEDs. And they buy their red LEDs from Asia. For other people like Lumileds and Osram, they generally tend to make their own LEDs and package their own LEDs. And in some cases, they may actually take a look at mixing and matching other chips, depending on price and depending on volume production capacity. So there's a lot of swapping and mixing and matching going around. I do not know to what extent Osram and Lumileds would do it, but in Korea and China, it happens a lot.
Perfect, thanks. We have a comment here, which there is an acronym that I don't know what that means. You might know, Bob. It's saying that the cost of attenuation and MTBF was not mentioned. Would you know what MTBF is?
Mean time before failure.
Perfect. Would you like to comment on that?
Tough question. It really depends upon how the LED fixtures are made. So the LED chip itself is remarkably reliable. And I'm going to go back to an earlier slide where I talk about the supply chain over here. And generally as a user, it's the mean time before failure of the fixture that you're really worried about. Now, you can get a failure of the LED chip, you get a failure of the LED package, and you can get a failure of the driver electronics going into the fixture. My experience with solid state lighting, and I presume it transfers to fixtures as well, is that almost all the failures and limited lifetime issues that people have with fixtures happen not at the LED level, but at the fixture level. Drivers fail, solder joints fail. These are some of the things that fail. You can also get failure at the package level. Those silicone lenses can discolor. Somebody might have pushed on it. There may be some ESD event. The LED die itself is typically very, very reliable, and it will age gradually. Under perfect conditions, where the package is very good and the fixture is very good, the mean time before failure of the LED is that, well, actually it doesn't fail. It just gradually gets dimmer and dimmer with a reduction in output power to, say, a 70% of original value level of anywhere from 50 to 100,000 hours. The chip is really very, very reliable. Once you put it in the package, the aging can be somewhat faster, but we're talking about reduction in light output that is gradual. Very, very little in the way of filamentary failure where it just blinks off. Lifetimes there are probably in the 50,000 to 75,000 hours. The fixture, anybody's guess, depends on how well it's made. And it really depends on how well you can solder the LEDs onto the board, how well you solder all the wires together, how well the driver is made. I would say that, at least from my experience in the solid state lighting world, where you buy an LED light bulb or you buy an LED lighting fixture and you put it into your office or into your building or into your lamp, almost all the failures are related to a failure of a non-LED component, either a solder joint or a driver. And there, the mean time to failure, it really depends on the quality of manufacturing. I've had solid state lighting fixtures that we've installed here at RPI that have been on 24/7 for 10 years and a very, very low failure rate. I've had other ones that fail within a couple of weeks, usually because of a solder joint.
Perfect. Thanks, Bob. There is one interesting comment here. I just would like to get a clarification. I don't think the point was very clear. Someone was asking, how can full spectrum LEDs promote vegetative growth if they do not contain blue light according to the image? I think one of the slides you show, you're talking about phosphorus conversion. And I think if you can clarify, phosphorus do not produce the blue light, but you do have some blue light going, right? So full spectrum LEDs, they do provide, at the end of the day, they will provide some blue light. Is that correct?
That's correct. In all of these diagrams over here, the blue light is coming from the LED chip. There are phosphors that can fill in this gap. These are just some representative spectra by using different kinds of phosphor materials to convert the blue light to other colors. And one thing I did not mention is that when you use blue light to make other colors, that drops the efficiency. The energy from the blue photon is high. The energy in the red or the yellow photons is lower. That light gets lost that energy gets lost as heat. But full spectrum, you can engineer this to look almost just like sunlight. In fact, Seoul Semiconductor has been looking to sell a Toshiba phosphor blend, and they call them sun-like LEDs. And they've been trying to push them in horticulture as being the closest thing to sunlight, sun-like. I don't know what kind of traction they're getting with those LEDs in the horticultural market, but they're advertising it as claim to fame. They actually use a blue pump down over here at 405 and then phosphorus to generate all the light. Not very efficient, but they're seeing what they can do with full spectrum.
Yeah, and I've seen Nichia advertising some sun-like spectrum as well, just to add to the mix. Another question here, Bob, was a comment saying, and that's a good point for discussion. You mentioned somewhere that the efficacy of 4.6, well, there was an efficacy to be reached of 4.6 micromole per joule. So people are saying that this is super high considering to the fixture efficacy available for horticultural lighting today, which is about 2.3 to 2.7. So if you can comment a little bit on how much of this gap do you think we can close going from where we are now, 2.3, 2.7 on most available LED fixtures for horticulture. Some of them claim higher efficacies, to get to this 4.6? Do you think we're going to be able to get there, considering everything, right? Lenses, fixture, drivers, or is this a gap that we can fill, or are we going to get close to that? What do you think would be in the future?
Well, you know, the theoretical efficiency in terms of micromoles per joule is when an LED can convert every electron you put in to a photon out, 100% operating efficiency. And the theoretical limit for that is between 4.6 and 5.1 micromoles per joule at 100% efficiency. The number, if I took this 4.6 micromole per joule efficiency that we have over here, which is measured at the package level for this OSRAM, new OSRAM red light emitting diode. By the way, this number can't be hit in the blue. It's probably going to be lower. And you put it into just the fixture with optical and thermal losses. Expect to derate that by about 75 to 80%, possibly more, depending on how well the fixture is made. That will take you down to the 3.5 to 3.7 microjoule range just for the red. Blue, if you add full spectrum and in phosphorus, that'll drop that even more. So if I had to make just a gut guess, we're going to see gradual increases in the micromole per joule for the overall LED fixture from kind of like the vicinity of around the high 2s into the low 3s, but probably no more than about over the next 5 to 10 years up to maybe 3.2 to 3.5, just because it's going to be really, really hard to make really efficient drivers, have very, very good thermal management with the possible exception of water cooling in greenhouses. And there are some people making water cooled fixtures. The driver losses aren't built into that number. So my guess is that, at least for the time being, the very rapid increase that the horticultural industry saw from, say, the high 1s, 1.7, 1.8, to maybe around 2.7, 2.8 right now, that's pretty well leveled off now. I don't see it getting much better unless we can solve some of these wildcard efficiency issues in blue LEDs and maybe continue to improve the manufacturing of the optics and the driver efficiencies. But there's not much upside.
Great, thanks. We are getting close to our 1 hour webinar. I just want to make sure there are 2 very nice questions here. I would like to touch a little bit on that, Bob, and if we can go a few minutes after that. So let me just lay these questions up, so if people are interested in hearing the answers and the discussion, they can stay in for a little bit more. One of them is about risks and needs for protection, so eye safety. You might have some good information from the general world, lighting world, so if you can talk a little bit about that, needs and requirements, human protection and safety operating under these high power LEDs, high light intensity. And the second one would be and we got several comments about this, how much time or what else we need to see in the industry for the complete replacement of HID fixtures in greenhouses by LED fixtures, considering costs, efficiency, and what else can we go, which other benefits can we get out of those fixtures. So just so as you know, the attendance, we're going to be talking about these 2 questions. Bob, if we can cover them in about 5-10 minutes, that'll be great. So then we can respect the attendance time as well. Let's start with the first one for human health. Do you have any, I know you didn't talk about this here, but that's a question you get all the time. Where can we find more information about these? Are you aware of any regulations that are existing in the general lighting that it could bring into the horticultural world? So
I'm not an expert on eye safety. I can relate my opinions about some of this, and that is that, and this is probably a fairly naive approach, but human beings have been existing under sunlight, which is really pretty bright, has wavelengths all the way down to 300 nanometers. People get sunburned, of course. But people have existed outside in normal daylighting for a long period of time. So generally speaking, at the light levels that people are exposed to in their normal everyday work from sunlight, eye safety is generally okay. Now, there are some long-term studies that suggest that people who spend a lot of time outside tend to have a higher percentage of long-term macular degeneration. But these studies for lighting, people are still doing research in this particular area. That being said, people are worried about things like blue light hazard, looking at LEDs with a lot of light. And I would say that ordinarily, the biggest challenge for some of the LED lighting right now is on people is going to be on human circadian rhythms with blue light, not getting a lot of that blue light at the night, things of that nature. And I say that ordinary eye protection, if the lights are really bright, sunglasses or goggles would be fine. But this is an area where more research could be done. But I always go back to the old standard. Sunlight's been with us ever since humans came around, and they didn't automatically go blind after a few years in the daylight.
Do you know any source of information, Bob, that people can find? UL would publish anything about human safety?
The human safety primarily has been developed by the Europeans in terms of overall light flex levels, because unless if you're not including UV, this is probably a true statement. It's very, very difficult to get light levels that can damage the human eye unless you're staring directly into the light fixture. There are European standards that deal with light levels and eye safety, and I don't have them. I can't quote them off the tip of my tongue right now, but they are available primarily from the European Union. But it's a hot topic. It's been a hot topic in general illumination. I can try to get them to you, Erica, and we can talk about them in more detail. I just can't do it right now.
Perfect. Well, that's great. And if you want to learn more about this, please send me an inbox message or email, and we can follow up on that. You receive a follow-up email from this webinar. Just reply to that. My information is there, and we can provide you more information around that. So there is another set of questions, very interesting. We're talking about, in general, I'm just compiling all the questions. You mentioned in here, Bob, that we cannot expect too much cost reduction for the LEDs. They're approaching their maximum efficacy. The costs of manufacturing will not drop too much more. So people are asking here, what should we expect as far, or time frame, or what else can we do as far as system and controls to improve and get more value for the growers? If the costs not going to change much, where can you squeeze more value and gains so then you can completely see the replacement of HIDs and LEDs in the greenhouse world? One thing I would just like to add here, you talk about the fixture level and systems considering driving, lenses, secondary optics. There's also controllers. LEDs, they can be controlling in a much more flexible way and provide much more benefits than the HPS. You can control the spectrum, you can control frequency, and you can integrate with other sensing capabilities into a greenhouse. So I think that's a huge area of improvement there, considering environmental sensing, plant sensing, and integrated controls that will take us in the direction of the full replacement of HIDs by LEDs. But Bob, would you like to comment a little bit about that?
So I think that the best approach is going to be for the conventional fixed spectrum. Horticultural lighting is just continued competition in the lighting space and gradual adoption. We saw this in the solid state lighting industry when, if you wanted to buy a high efficiency replacement for fluorescent light in the office, it was really, really very, very expensive. But through competition and basically consolidation of the industry and volume increases, the costs were dropped out. The biggest improvement in cost is going to be, unfortunately, in my opinion, at the expense of the margins that the horticultural lighting guys have right now for their light fixtures. And that's where that's going to come from. So you can buy very, very cheap LED fixtures for general lighting right now because they're making them by the hundreds of thousands in China. We get to that point, those kinds of volumes, it's going to be much more cost effective, but there's going to be almost no margin for the lamp manufacturers. That's going to come with adoption and consolidation in the industry. In terms of the controls and other kinds of things, that is going to be a very interesting thing to watch. I'm hopeful that in some areas, optimizing the spectrum and optimizing the control can yield major improvements in plant quality, nutritional value, growth rate, customization. Some of the people working with spectrum right now to have lettuce and leafy greens with designer flavors controlled by spectrum. That's really interesting, command higher margins. But those kinds of control capabilities are ultimately going to be determined by how we can get to higher levels of, say, kilograms of produce per kilojoule of energy. And if we can really increase the biomass efficiency by tailoring the LEDs, then I think that with better controls and continued developments in understanding the role of spectrum in plant growth, if there is a future there, it will be in maximizing biomass efficiency. Some of the pulsed work I talked about looks really exciting. There may be some things in spectrum that are going to be interesting, but this is where I need to hand it over to people that really understand plant biochemistry. I'm a semiconductor chip head, so I have to leave it right there.
It's a perfect combination, Bob. Yeah, and I think just to add a little bit to this, greenhouses, they have a very variable lighting condition. If you rely on the sun, you can have cloudy days, rainy days, very sunny days. Then you have your controllers on CO2, temperature. You have people across US, they grow different crops. So I think the LEDs, they allow us to have a much more flexible design for a lighting system than would an HPS light or HID lights, the metal highlights as well.
Yeah,
I think that we can really build on that.
Absolutely. The dimming is a lot easier. And by the way, that can leverage standard daylighting controls for indoor lighting just to compensate for total flux based on daylight levels. That control is easy.
Absolutely. So, Bob, let me get the last question, if you can briefly comment on that, and then we have to get going, which is a question about you provide information how the efficacy is approaching their limits. So the question is, can we expect other areas of improvement? And if you can comment on thermal management when purchasing individual diodes to build LED fixtures. So just narrow down the question to thermal management. Can we expect anything on thermal management?
Well, I'm a big fan of water cooling, but that's a system level issue. A lot of greenhouse growers won't be able to adopt that in their standard places. But that drops a lot of the cost out of the LED. You might be able to get better lifetimes by keeping the package cooler. You don't have to pay for the heat sink. You don't have to pay for the fans. You don't have to worry about fan failure. LEDs are very thermally sensitive. I know that plumbing introduces other hazards and difficulties, but I'm frankly optimistic that water cooling for high power fixtures in commercial greenhouses can be actually incorporated ultimately into the greenhouse mechanical or structural elements itself. And so I think there's a lot of upside in terms of taking a top-down systems level approach to improving thermal management by making the thermal management an integral part of how the greenhouse itself is built.
All right. Well, thanks, Bob. I appreciate everybody staying here with us for this extra 10 minutes. We still have questions coming, but unfortunately, we cannot go over the time. So please follow up with me by email. We can get these questions answered. Bob, thank you so much for being a presenter today. That was a very interesting topic, great discussion. Would you like to provide any final comments or thoughts?
Just one, and that is that I'm really excited about this application of LEDs in horticulture. I think we're just scratching the surface of some interesting things that we can do. Yes, the costs are going to come down a little bit more. The efficiencies are going to going up a little bit more. But I think it opens the doors for a whole lot of things that are going to be really important, especially as we approach a world, now I'm looking out in the future, with climate change and even more challenges. for keeping the world fed. So I'm really excited about this area, and it's fun to be working on LEDs for plant growth.
Thank you so much, Bob. Thanks everyone for staying here today with us. And I look forward to seeing you again on our next webinar. Have a great weekend, everybody. And we see you again on the next presentation.
And here's your next webinar slide, Erico. And just people still left. I'd never made it to that.
Well, it was good. We're kept busy through a very good discussion. So the next one will be on horticultural lighting systems energy savings calculations on February 20, 2 to 3 p.m. So same time, and I look forward to seeing you on this new presentation. Thanks everyone, and have a great day. Bye-bye.
Bye-bye.